So, translators is our next topic. There's a worksheet with lots of genuine past paper questions on it. Yeah, this is kind of where, well, actually this isn't the order, but this is, so translators is the topic that we're going to do now. Our next topic, by the way, is going to be databases. Mainly because you need to do a project in databases. Well, some of you have to do entity relationship diagrams for your project, so I'm going to teach you databases next, which is why the order is all muddled. Anyway, so recall. So this leads on nicely from our previous topic. If you can recall that we've just done assembly language, we've talked about low-level CPU architecture, all the different registers, the fetch, decode, execute cycle, exactly what's happening on within the CPU, and how it's working. And how to program for it, therefore. How to control the CPU at insanely low level, and then the next level up is assembly language. So we don't look at the noughts and ones, we look at the assembly language. And one instruction assembly language is one instruction in machine code. Yeah? So if you could recall that. To convert from the human readable code into the machine readable code, well, with assembly language, we went through an assembler. Again, this is just recapping, though you do need to know this, so it is worth remembering. In fact, and this is, you do need to know this still. So to get from your assembly language into machine code, well, the first thing you need to do, given that all you've got right now is your assembly language, the first thing you need to do is sort of reserve some space for your machine code. And then you take one of your mnemonics. What was it, the mnemonic? We have just done this. What's the mnemonic? Well, we did this the last lesson. This was what you did the test on.
Human readable, understandable form in which you can replace code so the person looking at it understands what the code does.
Yes.
In the assembly language.
Yes. So say those first 5 words again.
Human readable form.
Yes. It's the human readable form of the noughts and ones, basically. Good. So the mnemonics are the human readable forms, the human readable form of the machine code. It's like noughts and ones converted into letters that make a bit of sense. Symbolic addresses, if you remember, were memory addresses that were given labels to make them easier to remember. And the symbol table basically matches those labels to memory locations. So that's what the assembler does. And and this is what an assembly language program looks like. So we have, so my loop is a label, and then mov AH, and then there's a memory location, and another memory location. And so on the left of each of these, you have your mnemonic, and on the right, you have your either your data, your memory location, or a label of some kind. Like JMP my loop, you have your instruction and a label, and then elsewhere you have different things. So, translators. Well, these are. Actually, I'm going to pause this for a moment, if you don't mind. Okay, no, that's fine. It is actually interesting. Okay, so translators convert source code to object code. That's what they do. The source code is the human readable code, and the object code is the computer readable form of the code. So this is very similar to what we've looked at already. You have code that humans can read. We used to call it assembly language, but assembly language is still pretty hard for humans to read. So generally, when we talk about higher level languages, we have source code. We call it source code, and that is much nicer, much easier to digest. And it gets run through a translator of some kind, and we end up with object code. And the object code is the computer, is the noughts and ones, what the computer understands. The phrases object code and machine code are pretty much interchangeable. In some questions, the examiners use both. Sometimes they only say object code. There may be occasions where they only say machine code as well, though They seem to use object code more. So that's what I've used, but object code effectively means machine code. So translators convert source code to object code. There are two different types of translator. There are compilers, and there are interpreters. And they are different. There's also intermediate code, which runs on a virtual machine, and we look at that as well. So all of this initially might make you go, okay, that's lots of words. Don't panic too much, because all will be explained in a nice, easily digestible podcast format. So, translator. Compiler is a type of translator, an interpreter is a type of translator. It's easy to get the words interpreter and translator muddled because, like the UN delegate had an interpreter, had a translator. In that context, it seems that the words translator and interpreter are interchangeable. Though in computing land, an interpreter is not the same as a translator. An interpreter is a type of translator, and a compiler is the other type of translator. So, compilers you won't muddle, but translator and interpreter you might get muddled. So be clear that translator is the generic term for both compiler and interpreter. Clear? Good. So, what's the difference between a compiler and an interpreter, I hear you ask? Well, glad you asked. A compiler takes all the source code at once, thinks about it very hard for a very long time, and then generates generates your object code in one massive lump. So your compiler takes all the source code at once, thinks about it for a very long time, whirs and grinds and uses up all your RAM, and then comes up with an error message. Or it will actually generate your object code, assuming everything went according to plan. And then you run it and find it doesn't do quite what you expected. These are all the joys of logic and reasoning and programming. But yeah, a compiler takes all the source code and then generates all the object code in one massive motion. An interpreter, by comparison, takes one instruction from the source code and then makes one instruction in the object code. It then takes the next instruction in the source code and then creates the next instruction in the object code and then runs it immediately. I should probably mention that. So it takes one instruction from the source code, converts it and runs it. Then it takes the next instruction from the source code, converts it and runs it. So with a compiler, you're just running the object code. And whenever you run your program, you just use the object code. With your interpreter, every time you run the program, it takes the first instruction, converts it, and runs that instruction. Then takes the next instruction, converts it, and runs it. It basically converts it every time you run the program. Your interpreter converts your source code every time you run the program. Whereas your compiler only converts the program once. Yeah? Does that make sense?
So there's a compiler and batch processor.
Yes.
Interpreter. Surely each code has to be written so that it can execute. Because if it's not, so is that the advantages of each one? Because some code you'll write, you won't want it to execute one line by line.
There are pros and cons of both approach. You are right. A compiler effectively just batch converts, and then it leaves you with the conversion, and the conversion is what you run each time. Your interpreter does it sort of real time. It reads an instruction and then converts it and then runs it. Then it reads the next instruction, converts it and runs it. As a result, your compiler, when you run a compiled program, you're running an executable or a binary file. You double click on a .exe or a .bin. With an interpreter, you click on a .html file or a .js file or some other form of scripting language. if you think of, I mean, HTML and JavaScript are still perfectly good programming languages, but they don't get compiled. You just sort of, each instruction gets translated on the fly when it's needed. And these are two pretty good, so C and C++ and Objective-C all gets compiled, and Java also gets compiled, although we'll come back to Java in a minute. But yeah, so C, C++, COBOL, most languages, when you think of traditional programming languages, you're thinking of compiled languages. HTML, JavaScript, and the scripting languages are interpreted. And that's the fundamental difference between your scripting language and your compiled language. And there's pros and cons of both approach. What's the big advantage that interpreters have over compiled languages?
Pressure's on now. Presumably, it's not going to take up a huge amount of RAM for a long time, so you can still do things well.
Yes, that is one big advantage. Interpreters take up much less RAM. I mean, even like the biggest, most useless web browsers will still only use 150, 200 meg when you've got like many tabs open. Your compiler takes a lot more than that, and also takes a lot longer than that. So yeah, your interpreter can be much smaller, uses less RAM. But what's the main advantage? What's the big thing about HTML and HTML5 and JavaScript and PHP? What's the main reason why everyone is really excited about these languages?
It's universal.
It's universal.
Different platforms.
Platform independent. That's exactly it. You write your program in Objective-C, it's only going to work on one platform. You write your program using HTML5 and JavaScript, it'll work on any computer that's got a web browser. Which means TVs, cars, anything. So there we go. Interpreters. There are other advantages as well, and this is the mark scheme dumped on a presentation slide. Yeah, what you can see, and we'll discuss those in a minute. Oh, sorry. So there's some obvious advantages to this. Why is it an advantage to have the source code hidden? So, say again? So people can't steal it. People can't pirate your code. With Windows, I mean, Microsoft basically have their whole business based around the fact that their source code is totally hidden. No one can find it. So they sell you a CD or DVD with the compiled code on it, just the executable, just the binary code. They won't let you see the source code, as opposed to open source, and that's what open source means. So you can download the executable file only, like you do with Firefox most of the time. But if you're a developer and you want to make a new web browser that's based on Firefox, you can download the Firefox open source code, tweak it a bit, and then make your own version of Firefox and call it Fire Lamb, Fire Badger, or something. Flaming Badger, that'd be a good one. Yeah. So for many companies, the ability to hide the source code is a big advantage. And if you're a web developer, you might find it really annoying that people can go to your website and go, "Oh, that's nice," yoink, and then reproduce it exactly the same on their website. They can steal your JavaScript, they can steal your HTML, and just reuse it. So this is perhaps another one of the limitations of HTML5 and JavaScript. Something to bear in mind if you are a developer. Any of the web apps you make is going to be very hard. It's going to be even harder to defend your IP. And as we've talked about earlier, it's already pretty hard to defend your software IP.
So PHP.
Yes.
That's obviously hidden.
A
Can't really
bit.
Bit than like most people. How comes JavaScript 5 don't the same thing?
PHP is a script that gets run on the web server that tells the web server how to automatically generate HTML. PHP is basically a list of rules that tells the web server how to generate HTML. And it's only the HTML that then gets passed on to the users.
Oh, right.
Whereas with JavaScript and Flash and everything else, you literally download the whole file. You download the raw JavaScript, and then it runs the JavaScript and it sits in your temporary internet items as JavaScript. In reality, your PHP is still a .php file sitting on a web server, which of course is designed to allow people to be able to access and download web files. So it's still not that hard to steal other people's PHP. It's just a little bit harder because the web server doesn't give it to you. You just have to guess what the file name is. But even sometimes it will still tell you the file name. Platform independent obviously means it will run on pretty much anything. Optimized. What does that mean? Why is that there? How is that a big advantage? I suppose it's fairly obvious how it's a big advantage, but why is it possible with compiled languages not interpreted? Just think that through. Why can't you optimize interpreted languages?
Because they're platform independent.
Because they're platform independent, yes, which means
That they're all different, so you don't know what's going to work the most efficiently on them.
yeah, exactly. Because it runs on any hardware, it all needs to be there. The other thing is because, so yeah, that's definitely one reason, because it needs to be able to run on any hardware, it needs everything in there because it's not quite sure what it needs. What's the other big reason though? The other main reason why it's very hard to optimize your interpreted language. If you think back to this. Why is it basically impossible for an interpreter to optimize? And why your interpreted languages are always going to be slower. No matter how good PHP and HTML5 get, they're always going to be slower. No matter how good the new JavaScript engines are, they're always going to be slower than a compiled language. Because?
Is it because they're executed line by line? It means that
Yes.
they can't be optimized in a certain way because they're still going to go in the same.
Yes.
Yeah.
I know where you're heading, and you're absolutely right. Because the compiler can read ahead in the program, it knows what's coming next. It can remove redundant instructions. It can remove pointless bits of code. Or it can, if it can see there's a more, so you've done this, then this, then this, then this, well, I could do that in fewer steps if I do it like this instead. It can remove unnecessary instructions is the key the main thing. We will talk about that in more detail later. So we've got compilers and we've got interpreters, and those are the main differences between them. And then we have intermediate code, which, I mean, Java was the original, I suppose, certainly the most successful form of intermediate code. Intermediate code is code which gets compiled and interpreted. It was an attempt to get the benefits of both worlds. In reality, it just sort of sits somewhere between the two. Neither as fast as a purely compiled language, nor as platform independent as an interpreted language, though it almost was for a while. Java used to be a lot more platform independent than it is now.
How to make went backwards.
The short answer is Microsoft. Microsoft didn't invent Java. Java was invented by Sun Microsystems, and they said, it's a platform-independent language. It will run on anything. Look. And then Microsoft went, oh, that's not good. Why didn't we think of that? Well, how do we cripple this? And the Java virtual machine that came with Windows wasn't quite right. It didn't fully support Java, and so Java programs would run fine on everything except Windows, which, given that Windows had a mighty 5% market share at the time, was a bit of a bad thing. Sun sued them, and Microsoft went, all right, Microsoft said, Sun said, you can't call that Java. There's not a Java virtual machine. You haven't built a Java virtual machine. And then Microsoft said, well, it's kind of like Java. All right, we'll call it J++. And Sun went, no. And they went, all right. And then they spent a bit longer, and it turned into C#. And that's kind of where C# came from. It was originally J++, and then originally Java, and it's Microsoft's version of Java that only works basically on Microsoft's systems. And in the meantime, like, the Java virtual machine in Windows just got worse and is now a bit poor, and so Java programs don't run very well on Microsoft Windows systems, and you have to install programs. And but originally, it actually worked reasonably well. It was at least platform independent, though it's still not quite as fast. So it's interpreted. So source code, you have your source code, you have the Java source code. It's compiled by NetBeans into intermediate code, and then it's interpreted by the virtual machine the Java virtual machine into object code. I should probably put compiled by NetBeans in there. So that's why you have your two-stage process. Can I write NetBeans on this? Is it going to let me? It is. Or Eclipse. I suppose technically it's the Java SDK, but this is using Java as the example, by the way. I don't know which one they're thinking about. They're just thinking generic. So none of the exam questions or answers refer specifically to Java. They just call it intermediate code and a virtual machine and compiler. So NetBeans is your compiler, and then the Java virtual machine is your interpreter. They do talk about virtual machines, though. The Java runtime environment is the same as the Java virtual machine. It's quite nifty, that, isn't it? One of the interesting things about this course, it reveals things which you kind of, oh, that's why. So, that's the three main ones, and these are all the advantages of intermediate code. It's still platform independent, but it's been compiled, so it's error-free. Well, although, you know, as Matt says, not actually error-free, it's just, it's syntax error-free at least. Free of syntax and lexical errors. And in theory, some runtime errors such as div0. But that doesn't mean to say your program's going to behave the way you expect. Logic errors will still be there, probably. And it also hides your source code, and there's all the other advantages of a compiler. A random fascinating fact. Java runs quite slowly because it also gets interpreted. Your Java code isn't as fast. There's another disadvantage of platform independent languages, because they need to have this extra, they have to have this emulator, this virtual machine. You're still writing, sorry, I'll give you a sec. Because it has to have this extra layer, it needs to basically have this program sitting between, so a program that takes the Java, converts it into a different set of noughts and ones, so that it can run on the native hardware. That's what the virtual machine does. Theoretical or emulated computer on which your program can run. It's a bit like Word, I guess. Like a doc. Your computer, your CPU doesn't understand what a doc is, so you need to have Word that will open that file type and tell the CPU what to do with it. A better example, has anyone ever installed like a Mega Drive emulator or a MAME emulator or N64 emulator or a PS2 emulator or something? Obviously for a system that they own using the ROM which they extracted from the from their own system. Yeah, of course, good. And the BIOS as well, you have to extract the BIOS because the BIOS is also copy protected software. Yeah, good. But yeah, it's entirely possible to run, like I have a PlayStation 2, and I did extract the BIOS from my own PlayStation 2, and I was able to run my PlayStation 2 games on my laptop through the PCSX2 emulation program. I'd put in my disk, and the software would read the disk, and the software was written for the PlayStation 2, for a RISC chip, for the Emotion Engine, for an entirely different CPU. But this program allowed my Intel Core 2 Duo and its graphics card together to pretend to be the PlayStation 2 Emotion Engine. So I could play PlayStation 2 games on my laptop. The catch is that my laptop is a 2 gigahertz dual core system, and the PlayStation 2 is a single core 300 megahertz system. Yet my laptop could only just play these games at a sensible frame rate, because my laptop wasn't very good at pretending to be a PlayStation 2. And that's basically what's happening with your virtual machine. Your main CPU is pretending to be a Java virtual machine. But it isn't, it doesn't have the same registers, it doesn't have the same ALU, it works in a totally different way, it has a very different instruction set. Basically what an emulator is doing, what your interpreter is doing, it's like taking one instruction in assembly language, converting it into a different instruction in assembly language before then converting it into the machine code that can get run. Slows it down a lot. It looks at one instruction and thinks, well, I don't have that instruction on this CPU, but I've got these 3 instructions which are kind of similar. And it's a bit hit and miss, and it doesn't run very fast. With one exception. So that's true, and that's all on the mark scheme. The exception is Android mobile phones. Google wanted to use the Java programming language for their apps, and they went to ARM, who were building all the chips at the time, and still basically do, and they design all the chips at least, and said, so can you, like, we want to do our programming in Java, can you basically have some hardware that accelerates these Java apps? And ARM kind of went, well, we could, I suppose. We could basically build a small coprocessor that can accelerate the instruction set of the Java virtual machine. And so they did, and then basically they built a coprocessor, which is effectively a Java actual machine. It's no longer a virtual machine, it's a Java physical machine that is a coprocessor that comes with every Android handset. Which is why despite being especially some of the earlier the earlier Android handsets, they had like 700, 800 megahertz CPUs, single core, but they can run Java programs at a reasonable speed because they're not emulated. They're being run at hardware on a coprocessor. It's another interesting link between the previous topic and the current topic. Apologise if you're not that interested, but I find it quite cool, all this stuff. Yeah, that's what a Java virtual machine is, and that's what a virtual machine is, and yeah, it basically interprets the intermediate code one instruction at a time. Right, I think this might be a good place to stop and let you answer some questions before I move on. And give you more new words. Let's solidify the ones you've got. So you can at least do questions, I think, 1 to 3 now on that worksheet. So have a crack at them, and then we will continue.